Good afternoon, everyone. Welcome to Tah Poe Seminar Series 50. So this is the first time that the Tah Poe Seminar is entirely online due to COVID-19 situation. Okay, but this doesn't prevent us from discussing physics. Okay, so for today's speakers, so if you have any questions during the talk today, you can type in the comment in the Facebook Live, and then after the talk, I will pick some questions as speaker. So our today's speaker is Dr. Teeraparb Chantavat. She is going to tell us about extreme primordial black holes. So let's just welcome him.
Okay, thank you, Dr. Ph.D. So this talk, right, today I'm going to talk about a very interesting object called primordial black holes. And then I'm going to explain what I mean by the extreme primordial black holes. Okay, here is the outline of the talk. So first, I'm going to explain what do we mean by primordial black holes and the difference between the standard black hole that we know and most importantly, why do we study them? And next, we talk about the observational constraint on the primordial black holes. And I'm going to digress a little bit about and talk about the structure formation theory and try to understand how the primordial black hole formation start at the early universe and how do we actually count the number of the primordial black holes. And next, I'm going to talk about the extreme value statistic and how we could use this kind of statistic to predict the abundance of the most extreme primordial black hole, and also our formalism to perform the calculations, and finally our discussion, our conclusion. Okay, so primordial black hole is different from the standard black hole because, as you know, black hole actually formed by the collapse of the stellar type objects, right? So you have like a star or galaxies before, and then it's collapsed to form a black hole. But primordial black hole is actually created during the early universe or galaxy. So it must have been created from the extreme density part of the universe. Okay, and it's very interesting object because, as you know, that we have a lot of successful story in theory in physics. For example, the theory of gravitation by general relativities and the quantum mechanics and thermodynamics. And black hole is a very interesting object because in order to understand black hole, you need to understand all of them, like GR, quantum mechanics, and thermodynamics. And especially for the primordial black hole, because it's actually created at the early part of the universe, so it's connected to the theory of the early universe. And of course, I mean, from what we know from black hole, right, it's usually evaporated by what we call the Hawking radiations. Okay, so with the Hawking radiation, so what we have is that we can calculate the critical mass of the primordial black hole. So it's the mass that just before it would be fully evaporated. So basically, it will radiate it and then it starts losing its mass. Up until certain point, it just disappears because it's passed beyond the critical mass limit. So we can work out what would be the critical mass, just give you some kind of a rough approximation. So our calculations give us that the critical mass would be about 10 to the 15 gram. So we would expect that we wouldn't be able to observe primordial black hole below this mass, right? Because it should, I mean, in theory, evaporated already in the universe. But this is what I would call a pure primordial black hole, because the primordial black hole itself can increase its mass through many different astrophysical processes, like the mass accretions or the merger. So, but anyway, so this gives you the minimum mass that you would expect it from the primordial black hole. And as you can see, that it's changed with time, so it increased with time. So we can work out what would be the minimum mass of the primordial black hole at different epochs in the universe. Okay, now I'm just telling you about the motivations of studying primordial black holes, right? But why do we study them? As you know that we have a problem with something that we call dark matter, because something that you don't know. So primordial black hole would be a possible constitute of dark matter, but unfortunately the observation tell us that it doesn't comprise totally of dark matter. So dark matter cannot be comprised of fully from the primordial black hole. So what we would be interested is that how much the amount of dark matter that actually contribute to the primordial black holes. And it's very interesting because if we have the primordial black hole is also the speed of the massive black hole that we observe today. And it could explain many of the phenomena that we observe, for example, the late formation of galaxies. And it's kind of a good news because we could somehow or indirectly detect the existence of the primordial black hole through some astrophysical process like the weak lensing or the femto lensing, for example. Okay, so I mean, because we know that dark matter cannot be comprised totally of the primordial black hole. An interesting question would be how much primordial black hole would contribute to dark matter. So this is a few parameters that we will discuss throughout the talk. So we call the primordial black hole fraction. So it's defined as the ratio between the amount of primordial black hole to dark matter. Okay, and of course, I mean the distribution of primordial black hole could also depend on the mass. So which means that the different mass could have a different proportion or different fraction of the primordial black hole. So we define what we call the mass fraction. So it's the fraction of the primordial black hole that depends on the mass. And there are many different models that tell us what would be the distribution of primordial black hole with mass. For example, we could have a monochromatic model, right? Which tell us that the distribution should be just a constant, right? It's like a uniform distribution. Or a log normal model that is distribution like a Gaussian curve, but in logarithmic mass. And also a power law model, right? So in all this model, right, the monochromatic model and the power law model, you need to define the boundary, right? What would you expect to be the minimum mass and the maximum mass of your primordial black hole? Okay, so this is some kind of observational constraint, right? So we could constrain the amount of the primordial black hole fraction through many astrophysical processes. Okay. Okay, I put my pointer. I hope that you can see the pointer here, right? So the left purple shade is constrained by the black hole evaporation. So I mean, it's the Hawking radiation. So we wouldn't expect to observe any primordial black hole around this mass range. Okay, and the next, which is like the red orange shade, is lensing. Femto lensing is like a weak lensing, but the wavelength is on the same scale as the Schwarzschild radius of the lensing object. So it's got some kind of like a resonance that it would get a particular type of diffraction patterns. And it turned out that the object that actually has the mass and the length scale which could create it femtolensing is the primordial black hole, right? And there are some other astrophysical processes like the neutron star capture. So primordial black hole could capture a neutron star and produce some radiations, as well as it gets absorbed or is absorbed by the warp and it's got by the warp explosion. So the observation that you observe this kind of radiation, we normally assume some kind of standard model of cosmology, and we would predict what would be the excess radiation that you think it should have, and assume further that the excess radiation could come from the primordial black hole. So we got the constraint for that. And there are many kind of observation that constrain the primordial black hole fraction. And okay, so this is for the monochromatic, like mass fraction, right? But if you change the mass distribution into other model, right? For this one is for the log normal, right? And of course, I mean, is the constraint is very sensitive to the mass fraction model. So if I change into the log model, right, the constraint change. Okay. And this one is for the power law model with the exponent equal to -1. Okay, the shape of the constraint is different, and overall, right, the constraint that we have, we only get the upper bound. You don't get of the PHB fraction. So it gives you the upper bound. What would be the maximum number of primordial black hole that allowed by the observations? Okay, and we will come back and talk about how we calculate the mass fraction of the primordial black hole later on. Okay, now so we talk about the structure formation theory, right? So this is how the structure that we observe come from. So it's actually come from a small fluctuation in the universe, right? In the early universe, and because of gravity, right, the fluctuation will increase, right? It will grow, and the gravity will amplify the amplitude, so it make the fluctuation even bigger and bigger. Okay, so this is the snapshot of the early universe, right? And subtract by the average already. So this is the early universe at redshift about 1,100. So it had a fluctuation which is very, very small, but it's still a fluctuation of about 1 in a 10,000. This tiny, tiny fluctuation actually start to grow and getting bigger, and it's become the structure that we observe today in the universe. Okay, so this is like this picture comes from the N-body simulation, right, for the dark matter, and you can see the clumsiness of matter like almost everywhere. Okay, And so this is not what we observe, right? Because this comes from an in-body simulation. You won't be able to see this on the Earth. But what we actually observe is that what we call the galaxy survey, right? You observe the galaxy and as well as how far away from us, and that gives you some kind of distribution of galaxy on the large scale. Okay. Okay, now because we have a lot of galaxy, right? So it will be impractical for us to describe all the positions of the galaxy in the universe. So we have to the overall distribution of matter using some kind of statistic. And the statistic that we use to describe distribution is called the two-point correlation functions, right? So it tell us what is the most probable separation between galaxies, right? So basically, if there is some certain mechanism that prefer some scale of clumsiness or certain scale of like clustering. So this value will just show up, okay, in the two-point correlation functions. And if there is nothing, right, galaxy can create anywhere, right, anytime, without any correlation. So the two-point correlation function will be zero, right? It's called a Poisson distribution, which is truly random. Here, I'll give you some example. Like this is from the observation from the Salon Digital Sky Survey, right? And you can see that there seem to be some scale that represent the clustering scale of the galaxy. And that's actually called what we call the baryonic acoustics oscillations. Is the astrophysical process that happened at the early universe. So basically, anything that actually happened in the early universe affected how the galaxy distributed nowadays, and it can be probed by using the two-point correlation functions. Okay. And now we talk about the power spectrum. Power spectrum is just the Fourier transform of the two-point correlation function, right? And it's very useful. So it had a strong link to the initial perturbation in the early universe. So what I mean by a strong link is that if we quantify the fluctuations, right, of the matter, right, by something we call the density, right? So density is like how much the density fluctuated around the mean value, right? And of course, if we transform everything into a Fourier space and find the correlation function, it will give you exactly the power spectrum. Okay, so which means that if you measure the power spectrum, it also measures the fluctuations of the matters, the density, right? Okay, and that actually linked to the physics of the early universe. Okay, so now in the early universe, like we believe in something what we call the inflation theory. So it's the certain time in the universe that is expanded, right? And when it's expanded, it's created the fluctuation, which given by the power law model, right? We call it the primordial curvature perturbations. But we can just easily convert it into the density primordial perturbation by something we call the density and curvature transfer function, right? So basically, once we understand what is the power spectrum, we can trace back into the physics of the early universe, the mechanism, the process that happened in the early universe. So the power spectrum is quite important, and we will come back to that later. Okay, now once we got the fluctuations, like how the structure actually form, right? So we can think of the odicity, the fluctuations as a random walk. Okay, so it's gonna fluctuate with some kind of probability distribution, which we normally assume is to be a Gaussian. Okay, and so this is like and we have a threshold, right, called the critical density or the Koloff density. So once the fluctuation get beyond this value, right, so it means that it has a very high density. So it's likely to get collapsed into an object. Okay. And the variance of the fluctuations can be worked out if you know the power spectrum, right? So the power spectrum gives you the variance, and the variance gives you the probability of finding the collapse object. Once we know what is the critical density that would give us the collapse object. Okay, here is the very famous formalism, right? That's coming from the random walk of the density field. So basically, if you observe the number of the objects that created from some kind of Koloff mechanism, so for the small mass, it will behave as a power law, right? But once it gets into has some critical mass, okay, so it's M star in this figure, it start to drop. Okay, so which means that it's most likely to find small mass objects and is less likely to find a very extreme and a very high mass object because of the exponential decay. Okay, so I mean with the pressure formalism, we could predict the number counts of the Koloff objects by perform the integration over the cosmic value, right? And of course, we can compare with the survey because most of the survey don't cover the full sky, right? So we can just multiply by the fraction of the sky coverage, and you can predict what would be the number of objects that you observe for the survey, given the survey volume and also the redshift, and also the minimum mass that the survey can actually probe, because all the survey cannot probe the smallest mass. It has to have some kind of threshold mass that it will be able to observe. Okay, now once we got the formalism to actually work out the number of the collapse objects, okay, and now we are interested in something which is the extreme value, right? So what we are interested in the massive primordial black hole, right? Or the most massive object in a given observation. So basically, we could predict it, right? So we assume that if we have like the largest object, for example, with the radius r, right? What would be the probability of observing the observed radius r and less? Okay, by work out the cumulative probability distribution functions. Suppose that you have n observations, right? And you assume that these n objects, they are independent, right? So we can just work out by multiplying all the cumulative probability distribution function. And if you take the derivative of the function, you get what we call the exact extreme value PDF. Okay. So basically, is the probability distribution function of the most massive object in a given survey, given by the number of the object that we observe. And of course, I mean, in this slide, I use radius, right? But we can convert radius into mass. Okay, it's something pretty straightforward. Okay. Okay, now I'm going to jump a little bit back to the primordial black hole formation. So we picked some particular interesting model of the primordial black hole formations we call the log delta model, right? Is definitely motivated, right? Because if you understand inflation, right? Inflation is actually has an inclined slope. So the power spectrum is actually decreased. So it's unlikely to find a small and dense object, right? And it's very difficult to actually get a very large amount of power flow. But this model is interesting because it's predict that there will be some scale which have a sharp spike, right, in the power spectrum, and that could potentially be formed as the primordial black hole. So this is a model, right? It's depend on the amplitude, right? So like the size of the sharp feature on the small scale on your power spectrum. Okay. Okay. Now we have to relate it something in the early part of the world. So because the world expanded, right? So we have the scale that actually re-enter the horizon, right? And that particular scale, right? If you include all the mass of it, we call the horizon mass. Okay, and the numerical simulation suggests that the initial mass of the primordial black hole will be a fraction of what we call the horizon mass, and we can actually model it using only a few parameters. For example, so in this model, right, we set delta C equal to 0.45 and K equal to 3.2 and so on. So this is just come from a model and from simulation. So what is interesting is that we could have the horizon mass as the scale that re-enter the horizon, all of them, and we can work out the fraction of that part that could potentially become a primordial black hole. Okay. Now let's combine the log delta model with our extreme value statistic, right? So in this plot, right, I'll give you the exact value statistic, right? So basically, in different plot, right, we have a different number of observations, right? If we have 10 observations of primordial black hole, it would have a particular distribution. So in this case, right, you think that if you have like 10 primordial black hole, right, and you pick the highest object, the highest mass among the 10 of them, what would be the probability distribution of that largest primordial black hole among 10 objects that you observe? And you can increase the observation, right? You can predict it. You can draw about 100 primordial black hole and get the distribution of what would be the highest, the most massive primordial black hole among the 100 objects that you observe. And you can see that the distribution kind of shifts towards a higher and higher mass, right? And another thing that you can see is that it's not symmetric, right? It's a little skewed toward positive mass. So this is a kind of a feature of the extreme value statistic that has a probability that it can create an extreme object, right? It's not balanced basically. Okay, so the skewness is a natural feature of extreme value statistic. Okay, now, so once we got the model that we can predict the formation of the primordial black hole in the early universe, and how could we get the extreme value statistic, the mass fraction, we have assumed that the mass distribution of the primordial black hole should be monochromatic, right? Because of the model is a spike, right? So it actually doesn't prefer any particular scale, so it should be monochromatic. And once you take that monochromatic mass model into account, and we can readjust the normalization factor, okay, and so that will include the upper bound correction for the mass fraction, so that it doesn't go beyond the maximum monochromatic mass distribution. So that gives you some correction factor back into the primordial black hole fractions. Okay. Now we can work out. So in our model, right, we have two parameters. So the amplitude and the horizon mass, right? And we can convert the monochromatic upper bound, right, as a functions of our in our parameter space. And you can see that is so you can see that is actually prefer quite a small fraction, right? Below 10% mostly, but that would be the extreme value, right? That's the upper bound. Okay. Okay, now with this, right, we did some prediction, right? Suppose that we have 100 observations of primordial black holes, right? At redshift about 0.2. And we found that there is a strong correlation between the most probable extreme mass or the peak of the distribution, right? So it's got a real relationship, but it's got some scatter, right? In this case, right, suppose that we have horizon mass of about mass, we could get a massive black hole of about 30 solar mass, and that still be fine with the observational bound at redshift 0.2. Okay. So we combine all the current constraints, like, and predict what would be the most massive primordial black hole that we should observe as a probability distribution functions that still obey the observational bound, right? And of course, we just assume that the horizontal mass is 1,000 solar mass, right? So that's still some degree of freedom in our model, but we could predict what it should look like. And in the future, right, if we have a tighter constraint, for example, 50% tighter constraint, we can recalculate it and give you another probability distribution of the most massive primordial black hole. Okay, so I think I'm going to come into the conclusion. So we give some kind of like formalism to calculate the probability distribution function of the most massive primordial black hole, which we can compare with the observations, and of course when we compare with it, we can work out what would be the mass of the primordial black hole that's still allowed by the observations. And our formalism is still flexible because we can change the model, we can change the parameter to a different mass model and black hole formations model, and we can work out. So it's quite flexible. Okay, thank you.
Okay, thank you, Dr. Teeraparb. So actually, we have got two questions from our audience. So from Dr. Supakchai Ponglaskun. So I will let me read both of the questions. So the first one is, have primordial black holes been observed so far? And the second
Okay.
And the second question is, what kind of astrophysical signal that could potentially point out an existence of primordial black holes?
Okay, so the first question is very easy because we don't have observations of primordial black hole yet. Okay, that's answer the first questions, but as I say is theoretically motivated object to study because it's combined many interesting physics theory together. And for the observation part, I think I'm going to refer to this plot. Okay, right. So the only thing that we can observe is how the primordial black hole interact with stellar objects. For example, it could merge with a neutron star, right, and create an explosion that will cause a signal, right? But the problem is that a standard black hole would do just the same as the primordial black hole. So what we could do is that once we work out the radiations and we calculate what would be the amount of the signal that we would expect it from the standard black hole and predict what should be the excess amount of radiations. And we can assume further that the excess amount of radiation could come from the primordial black hole. So this is why this constraint come from. Okay, I think I hope that this answer the questions.
Okay. So there is no more question from the audience, but let's just wait for a little bit. But in the meantime, let me ask some questions. So on the slide 20, so you have made some use of random walk. So is this from the simulation or?
Yes, because we have some probability distribution functions, right? And we assume to be Gaussian, so it's a Gaussian random walk.
Oh, okay.
Okay.
And so you run it for many times, right? I mean, when you run the simulation once, you get this picture, right?
We actually don't because every information actually contained in the variance of the fluctuations. So we can work out the variance directly. Okay, you don't have to do any simulation. Is the variance can be calculated from the power spectrum, the primordial power spectrum.
Ah, okay. So this is just some illustration, but you can calculate things from theory directly.
Yes, from inflation theory. Yes.
Okay, thank you. Okay, so there are some more questions. So another question from Dr. Supakchai Ponglaskun. Do we have any constraints on primordial black holes mass?
I don't quite understand what he means, but this will because we only have the upper bound, right? That's the constraint that we have, and okay, so is the fractions, right? So basically, we don't have a so from the figure we don't have a direct constraint on the mass, but we only have the collective number of primordial black hole as a fractions of dark matter. Okay. I think that's it. We don't have concern for a single mass because that gives you so this will give you the statistic of large number of primordial black hole, but the sum of it shouldn't exceed certain limit.
Okay, and we have the next question from Dr. Chen. It's not the question, but it's actually the comment. I think people still argue about can GW190521 be a primordial black hole merger?
Yes, and I told you it's very difficult to distinguish between the primordial black hole and the normal black holes, right? Because it would just a black hole is have the same process, it had the same interaction with stellar mass objects. But that's a very good comment. Yes.
Okay, so we have got some further clarification from Dr. Supakshay Pongsaskun. So so the previous question, he meant that what are the mass range of primordial black holes that we expect?
Okay. That's good questions, but it's kind of depend on the horizon mass, right? If you actually look at this figure, okay, this one here, right? So we still have a free parameters called the horizon mass, and that would be the advanced. We know we input the horizon mass, we can work out the mass that would be a fraction that contribute to the primordial black hole, right? But it's still debatable what would be the mass of the primordial black hole.
Okay, there is no more question, but shall we wait for just a few seconds in case some people is typing? So if you have any questions, please type in the comment box and I will read it for our speaker. So I suppose that there is no further questions or comments. So let me let us end the this talk here. So let me thank our speaker again, and thank you everyone for your attention and listening. So
Okay.
we will we will be meeting again next time, and please for the next meeting we will be announcing later. Okay, so thank you very much.
Okay, thank you for your attention.